This is the second lecture where we are going to cover hypothesis testing across multiple samples. In Chapter 10, we concentrated on hypothesis tests concerning the means, and Chapter 11 concentrates on hypothesis test that compares proportions. So things look fairly similar here to the last video, and once again we have three different basic types of tests: left-tailed test, right-tailed test, and of course two-tailed test. And our null hypothesis under the left-tailed test is that the proportion of the population for population 1 that has some characteristic is greater than or equal to the proportion that has that characteristic in the second population. So P1 minus P2 is greater than or equal to 0. And the alternative hypothesis is, of course, the opposite. This would be our desired research result if we were formulating our alternative hypothesis in that manner. And so the alternative would be that P1 is actually less than P2, or P1 minus P2 is negative. For a right-tail test, we just swap the direction of the inequalities so that the null hypothesis is that P1 is less than or equal to P2, and the alternative that P1 is greater than P2. And then finally, with a two-tailed test, we simply have the null hypothesis that the proportion of the population with the characteristic is the same across the two different populations, 1 and 2, and the alternative is that they're not. So in this case, we have evidence against the null hypothesis with very large and very small values of the test statistic. So we just have to remember that we have two tails in the distribution. When we pick our significance level alpha, we have to remember that there's alpha 2 left over in each tail. So, of course, what we're concerned with here is the point estimate from the sample data, the point estimate of the difference in the two population proportions. And our best guess of that difference in the population is, of course, the sample difference. So the bars signify that these are sample proportions. They're calculated from sample data. And we have our two populations, 1 and 2, and that's really our point. That's our point estimate. So since it's a point estimate and we're calculating it from sample data, it's a random variable. So we need to concern ourselves with the sampling distribution of P bar 1 minus P bar 2. It's an unbiased estimate of the difference in the population proportions, but we also need to know the standard error of that estimate. And we calculate that with a very simple formula, one that looks a lot like formulas that you've seen before for proportions. P times 1 minus P multiplied by 1 over the sample size for the first sample, from the sampling from the first population, and N2 is the sample size when we sample from the second population. Now it's important to remember, of course, that when we calculate the value of our test statistic from the sampling distribution of P bar 1 minus P bar 2, we're going to assume that the null hypothesis holds true with equality. That's why the equality sign always shows up in the statement of the null hypothesis. And so we actually, under the null hypothesis, have two different unbiased estimates of the true population proportion, and that's both P bar 1 and P bar 2. And so the question that arises is, well, do we use P bar 1 in this equation, or do we use P bar 2 in this equation, or do we use some combination of the two? And what we're going to do is we're going to use a combination of the two, a weighted average of them. So this formula gives you a weighted average of P bar 1 and P bar 2. That's pretty obvious from looking at the formula. So we'll calculate that weighted average first, and after calculating it, we'll put it up here in our formula to estimate the standard error of the estimate. Okay, that will be the strategy here for combining the sample data to get an estimate of the true population proportion under the null when the null is stated with equality. Okay, so In this case, we don't have to worry about degrees of freedom. We're going to use the normal approximation to the binomial distribution again. And so we're going to have a z-score here. So we're going to use a z-score, and we've got our point estimate up here. And of course, we want more than just a point estimate. We want to express it in terms of standard deviation. So we have to divide it by the standard error of the estimate, which we talked about on that previous slide just a second ago. And once we do that, we've expressed the difference between the two sample proportions in terms of standard deviations. So we'll measure how many standard deviations from zero, right? Each null hypothesis when stated with equality is equal to zero. How many standard deviations away from zero we are when we calculate p bar 1 minus p bar 2. And extreme values in terms of how many standard deviations we are away from p bar 1 minus p bar 2, that's going to give us evidence against the null hypothesis. Either a very large value of z in a right tail test, a very small value of z in a left tail test, or either a very large value of z or a very low value of z in a two tail test. So I'm going to demonstrate this for you with a real quick example. We're going to pretend here that we work for a company called Market Research Associates. And we're going to do a hypothesis test at the 5% significance level. We're going to pretend that we've been hired by a firm in order to run an awareness campaign, a marketing campaign for this firm's products. And so what we're going to do is we're going to go out and we're going to sample households before we run our ad campaign, and then again after we've run our ad campaign. And we're going to ask households, are you aware of the client's products? And we're going to look at the proportion of households who claim that they're aware of our client's products before the ad campaign and after the ad campaign, and look for some statistical evidence that the amount of awareness has increased. Okay, so that we can claim that we've actually done a good job with our marketing campaign and that it was effective. We're going to try to establish that scientifically. Okay, so that means, of course, that we start out with step one by developing the null and alternative hypotheses. And I would point out that just keep this in mind. P1, right? That's the awareness after. We're going to make that the awareness after the new campaign. So P1 is the awareness after the new campaign, and P2, sort of the second population here, is before we run the campaign. And so when we state the alternative hypothesis, we're going to state sort of the desired research result, which is that we had an effective ad campaign, that the proportion of people aware of the product went up, which would imply that P1 is greater than P2. So that'll be our alternative hypothesis. Then we're back into our null hypothesis stated as the opposite of that, right? We really need to find a lot of evidence against the null hypothesis before we reject it. And our null hypothesis is that we had an ineffective ad campaign, that the proportion after is less than or equal to the proportion before. Okay, so clearly this is a right tail test. So step two, of course, is to pick the level of significance, and I picked 5%. So there's a 5% chance, if the null hypothesis is true, there's a 5% chance of rejecting the null hypothesis and concluding that we had an effective ad campaign when we actually didn't. Okay, that's step two. And then we have step three, where we go out and we collect sample data and we calculate the point estimate. And then we calculate the standard error of the point estimate. And we're really concerning ourselves in step three with the sampling distribution of our point estimate when the null hypothesis is true and is stated with equality. So we go out and we sample, before. We call that sample two. And we sampled 150 households. 60% said they were aware of the product. 60 divided by 150 is 40%. So P bar 2, right, that's equal to 0.4. Afterwards, what we're calling sample 1 here, we sampled 250 households. 120 claimed they were aware. That's 48%. So that's sample 1. So awareness went up by 8%. But that could just because of, that could be just because of sampling, right, and the variation that you expect with sampling, or it could be because the ad campaign was genuinely effective, and that's what we want to establish with our hypothesis test. So in order to do that, we will next move to step 4, and step 3 continued. Let's finish step 3 first, then to step 4 where we calculate the point estimate. Step 3 here is going to be to calculate the point estimate, the best estimate we have of the change at a population level, and the proportion of awareness is from the sample data. So it's 0.48 minus 0.4, an 8% increase. We calculate the standard error of that point estimate, right? And in order to do that, we have to start down here and calculate P. That's the weighted average of the 0.4 and the 0.48. So we have the 0.4, the 0.48, the sample size before and after, the 150 and the 250, and we calculate that weighted average of the proportion from the samples. And under the null hypothesis, both of those proportions are unbiased estimates. So we use all the sample information this way, and we take that and we plug it back into the formula for the standard error of the estimate, right there, and again right there. We've got our sample sizes, and we get the standard error of the estimate of 0.0514. We use the point estimate and its standard error in order to calculate the t-statistic. That's what I've been calling step 4. So the formula for the not the t-statistic, I'm sorry, this time it's a z-score. No degrees of freedom here that we have to worry about. We've got 0.08, and we want to express that in terms of standard deviation, so we divide it by the standard error of the estimate. Very good. We get 1.56. That means that our 8% difference is 1.56 standard deviations to the right of 0. And the question is that enough evidence from the sample to reject the null hypothesis and conclude that the ad campaign was effective if we're only willing to take a 5% chance of making a type 1 error and rejecting the null hypothesis and concluding that we have an effective ad campaign when we don't? Okay, so again, very simple stuff here. So in step 5, we determine whether or not the null hypothesis is rejected. And we have 2 methods for doing that. And I know that you're familiar with both of these by now. The first method that I'll cover is the p-value approach once again. Which method you use is inconsequential. It's up to you. Often a matter of convenience. But the p-value here is the area that's in the right tail at 1.56. So we've got some distribution. I don't have to be too fancy with the graphs. You guys should really know how to do this by now. I'm guessing that you're very good at it. You got 1.56. That's the value of our test statistic. So there's an area that's left over to the right of 1.56, and that's the p-value. We're going to calculate that p-value, and we're going to compare it to the level of significance. Okay, so that p-value, what I did was I went up, I looked up the area in a table that was to the left of 1.56. Actually, I think I used one of the Excel functions to do this, or maybe I did it in R, I don't remember. But you could just look it up on a table as well. The table gives you the area, the standard table typically gives you area that's to the left of value, so that's 0.9406. So I have to subtract that from 1 to get the area that's left over to the right, and I get 0.0594. And since 0.0594 is bigger than 0.05, I cannot reject the null hypothesis. I fail to reject it. So at least at the 5% significance level, we can't claim that we had an effective advertising campaign. The 8% jump in awareness is likely just due to the fact that you get different answers in different samples if you're only willing to take a 5% chance at making a type 1 error. Using the critical value approach, which is equivalent, we would just look up the critical value where 5% is left in the right tail of the distribution, and so that's going to give you 1.65. So you can look that up on a standard table or use a computer function like an Excel or R or Python or something, and you can easily find out that the critical value is 1.65. At that critical value, there's 5% of the area that's left over in the tail here. Alpha is 5%. Our test statistic is 1.56, so it's to the left of it. It's down here somewhere. And since 1.56 doesn't put us out here in the rejection region, again, we fail to reject the null hypothesis.